Are you ready?
I'm ready.
Okay, so I'd like to welcome you to this session with an invited talk by Andre Martinez-Finkelstein. Andre got his undergraduate degrees in Cuba, and then a PhD in Russia before moving to Spain and various places in the US, and is now currently based in Baylor, at present actually in Spain. So it gives me pleasure to invite Andre to give his talk on multi-applications of multi-orthogonality. But before Andre starts, could I ask you, if you have any questions, can you put them in the Q&A session? And then we'll deal with them as we go along. So over to you, Andre.
Thank you very much. Let me share my, okay, I hope you can see here my screen, Ray. Okay, so, well, thank you, Peter, for introduction, and thank you all for attending this lecture in the new format. It's kind of new. Of course, I understand it's a big honor to be invited to give such a lecture at such a conference, and I realized that my own personal merits do not play a major role in this decision. I represent basically a very vibrant community of researchers that work on orthogonal polynomials, special functions, or apply them in several areas of science and engineering. So this realization actually impacted my decision of the topic of this talk. So I decided to speak about something that represents interest of many people in this SIAM activity group. In this sense, I would classify this talk as advertorial. It's a word I learned recently. The risk of such a talk is that normally specialists will find very little new, and non-specialists will find overwhelming amount of information. But let me try, and in the worst case scenario, if you want to stick to the end, you can always, with this format, enjoy a beverage of your own choice without being seen. Okay, we start then with something that people probably know very well, orthogonal polynomials. It's a motivation of this talk for the beginning. So orthogonal polynomials, we know they're sitting at crossroads of several areas of mathematics. They're closely related to approximation theory, numerical analysis. They also appear as solutions to certain differential equations. There are certainly special functions in analysis, and it's related to certain three terms recurrence relations. They also solve important spectral theory problems, and all these connections make them very much applicable in mathematical physics, engineering, computer science, and other areas. Now, in the most broad sense, orthogonal polynomials I'll be talking about are polynomials of a single complex variable. So I'm not talking about matrix or any other more abstract polynomials. And they are orthogonal in the sense that we have certain inner products, can be even just a bilinear form in such a way that when we multiply this polynomial by anything of smaller degree, we get 0. And we impose additional conditions, then when multiply by polynomial the same degree, we get something different from 0. Now, this bilinear form can be given in terms of an integral with respect to a certain measure, a positive measure preferably. We have a complex conjugation, so it's actually an inner product. In this case, our orthogonal polynomials are connected to other problems. So for instance, they satisfy certain extremality problems in L2. So they minimize the norm among all the polynomials, monic polynomials that degree. We can write the reproducing kernels for these spaces of polynomials in terms of finite linear combinations, finite combinations of these orthogonal polynomials, and so on. Now, if we go more specific, for instance, and we assume that the measure is living on the real line, what we get are so-called orthogonal polynomials on the real line, or OPRL. And in this case, they immediately get a bunch of very important properties, extra properties. For instance, they satisfy one of the crucial effects, they satisfy 3 terms recurrence relations that can be organized in the form of a matrix. It's a 3-diagonal matrix, and this connects them to the spectral theory of self-adjoint operators. Or we can actually collapse this reproducing kernel formula in terms of finite number of polynomials to only 2 polynomials. This is so-called Christoffel-Darboux formula that has also very important implications. All the zeros are real and simple. They interlace for consecutive degrees, and this has implication for quadrature formulas, for instance. It also allows us for very effective computation of nodes and weights in terms of eigenvalues of Jacobi matrices or eigenvectors. They're connected to moment problem, Hankel operators. So in this sense, we could say that orthogonal polynomials are the modern analysis because they're connected with so many areas. If we narrow down further the measure and assume it's absolutely continuous with respect to certain nice weights, what's called semi-classical weights, we have more properties. We have so-called Rodriguez formula that allows us to obtain polynomials by differentiation, or we have the linear differential equations that are satisfied by these polynomials. And in this case, these polynomials actually solve 2 spectral problems, one for Jacobi matrix and one for this differential equation, differential operator. So they solve a bispectral problem. Now, we can have even non-Hermitian or indefinite inner product. In this case, everything becomes much more complicated. At the same time, everything moves to the complex plane. We use the power of complex analysis. So for instance, some specific case, we could plot the zeros and get absolutely beautiful pictures of the zeros that show they prefer to sit on certain nice curves, partially explained by the theory starting in the early 80s by Gonchar, Rachmanov, and Stahl. So let's move on to the multiple orthogonal polynomials as the main subject of this talk. Now, what are the multiple orthogonal polynomials? So I'll explain the simplest setup. So imagine we have 2 weights, in this case, W1, W2, and we have a multi-index with 2 non-negative integer values. So there are 2 types a priori of multiple orthogonal polynomials, type 1 and type 2. Okay, let's look at them more carefully. So type 1, essentially, we make a polynomial combination of the 2 weights. So we find coefficients, polynomial coefficient A1 and A2, limited by in degree by the elements of the multi-index in such a way that this combination that we call Q still satisfies the standard orthogonality conditions. So in other words, when we integrate, we multiply by any polynomial of degree 1 less than the number of free parameters. With respect to a certain measure, we get 0 and eventually non-zero for the next degree of the polynomial. This is type 1 when we combine two weights. So in this sense, I would call it like a combined philosophy for the type 1. Now, if we look at the type 2, it's a little bit the opposite, because here we have a single monic polynomial of degree, total degree n1 plus n2, but we divide the number of orthogonality conditions between two measures. So the n1 minus 1 orthogonality conditions correspond to the first weight, and the second, and n2 minus 1 orthogonality condition correspond to the second weight. So this would be kind of like a split philosophy. Same polynomial has two sets of orthogonality conditions. These are type 2 polynomials. We can also combine this and have polynomials of mixed type. I won't be explaining this, but they're also very interesting objects. It's enough what we have here. And if you count the number of equations, there's a linear homogeneous equation, you see that these polynomials always exist. Now, the question is uniqueness, or if we normalize as monic, then existence is an issue. So the multi-index for which these polynomials exist are unique, it's called normal. So normality, it's a serious problem in general. So they have several names. They are known by Hermite-Padé polynomials. You'll see in a second why. Multi-orthogonal or poly-orthogonal polynomials, d-orthogonal polynomials. It's like in Tunisian mathematicians use typically d-orthogonal. Polynomials simultaneous orthogonalities from Russian school, vector orthogonal polynomials, and many more. So let me start with this very simple example. It already appeared in a talk, if you attended the mini symposium we had before in Guilherme Silva's talk. So imagine you start with the polynomial, fixed polynomial of even degree and positive leading coefficients, real coefficients, and you pick two different values, C1 and C2, real values. Then it can be proved that for any multi-index, there is a unique monic polynomial Pn of degree m1 plus m2, such that these conditions of orthogonality are valid. So we see these are just type 2 polynomial, and these are our weights, W1, W2, just there is the same weight essentially up to a linear term in the exponential. So since it happens for any multi-index, so any multi-index is normal, we call this kind of systems perfect systems, when we have all the normal indices are, all the indices are normal. Okay, so this is an example of perfect system. Very particular case when the polynomial we started with, that's sitting in the weight is x squared. For x squared will be Hermite polynomial. This is a multiple Hermite polynomial, and for that polynomial we can write, for instance, analogs of Rodriguez formula, where what we have here in parentheses is a differential operator that we apply to the function e power negative x squared. Then we multiply back the result by e power x squared, we get polynomials. This will be my multiple orthogonal polynomials of type 2. Another feature of this polynomials is the recurrence relation. So let me remind you again, I'm back with the orthogonal polynomials, standard orthogonal polynomials. They satisfy 3 terms recurrence relation, right? That are linear equations on PNs and consecutive degrees that we can organize as, it's an infinite number of linear equations we can organize in a matrix form. On the left, we'll have x times the infinite vector of polynomials. On the right, matrix J times this vector of polynomials. Now, matrix J is easy to see. It's 3 diagonal. And it's symmetric. We call such matrices Jacobi matrix, right? So it looks like a equation for eigenvalues, right? It immediately relates to the spectral theory, in this case of symmetric or even better, self-adjoint operators, which is very nice because it's a well-developed theory. This recurrence relations also allow us to work out a lot of consequences. I mentioned already this CD or Christoffel-Darboux formula for reproducing kernels and many others. Now, multiple orthogonal polynomials, they still satisfy the nearest neighbor recurrence relation, but the bad news, it's no longer 3 terms. So for instance, if we look at this Q guy who was just this polynomial combination of 2 weights, it still satisfies a recurrence relation now involving 4 terms, and 4 because I'm only playing with 2 weights. So actually the number of terms will be 1 more than the number of weights. Sorry, 2 more than the number of weights. Same thing happens to the polynomial of type 2, P. It satisfies this recurrence relation with the nearest neighbors. But observe that here we have 2 parameters, N1 and N2. It's a multi-index, so we can vary, either we make a step in the first index or in the second index. So this was studied and first by Walter Vanesse, and you can find in his papers. So if we want to connect this with the theory of spectral theory, so option 1 will be, okay, we have to forget about symmetric matrices. We have to work with non-symmetric operators. That would be bad news because the theory of non-symmetric operators is much more involved and complex than the theory of symmetric or self-adjoint operators. Another difficulty, as I said, we have nearest neighbors now are 2-dimensional. So in fact, if you want to get from, say, the degree 0, 0 to the degree N1 and 2, unlike in the orthogonal polynomial case, which is 1-dimensional, here you have a lot of different options how to get there, right? So in fact, N1 and 2, it's not a single point on this rectangular or square grid. It depends how you got to this point. So it's better to represent it not just a point on the plane, but as a decision tree when each step that you make, you decide if you're going up or to the right. So in other words, all these points are basically points not on the plane, but on the tree. And that was the idea that Aptekerev, Denisov, and Yatselev implemented very recently, looking at these recurrence relations as relations on the trees, and then symmetrizing this problem. And then you get Jacobi operators on trees, which is very nice. It gives us this connection with spectral problems on more involved geometry, but still symmetrical self-adjoint operators. Let me insist that this is actually one of the origins of multiple orthogonality in practice is when you have recurrence relation of more than 3 components. I mentioned already that normality is an issue. It's very easy to understand, right? So imagine you're looking at a type 2 polynomials which have 2 sets of conditions, for half of them for W1, another half for W2. And imagine you just make W1 equal W2. You definitely don't have enough condition to have uniqueness. So you have to assume something else about the weights. And in general, there are 2 classes of weights that have been studied on the real line. I insist I'm on the real case. So we have 2 weights on the real case. One case is so-called Angelescu or Angelescu. It's a Romanian mathematician. He published, but the way he wrote his, it's a beginning, it's more than 100 years ago, published in a French journal, but the way he wrote his last name was Angelescu. And the assumption is that both weights, the convex hull of the supports of these 2 weights are separated, they're disjoint. So we'll weight W1 sitting on the left, W2 sitting on the right. This is one situation in which proving that all multi-indices are normal, so it's a perfect system, it's not difficult. It's quite standard. Now, much more interesting and more involved is the second case, studied by the Russian or Soviet mathematician Nikishin, who passed away very young. It's a little bit the opposite case when both weights are sitting on the same interval. But there's an extra condition that there is an auxiliary interval disjoint from that one, such that we have an extra situation there. The ratio of these two weights can be analytically continued all the way up to this interval, auxiliary interval, where it's represented as a Cauchy transform of a measure. So this technicality is not important. So essentially both sitting on the same interval, but the ratio satisfies certain extra conditions. Now, proving normality in this case, and even more, proving that it's a perfect system was a big open problem. It was a challenge and was addressed and recently completely solved by Ulises Fidalgo and Guillermo Lopez Lagomasino in the case of Nikishin system. And normality in this case. Now, of course, when I chose subject, my own preferences dominate. I like analytic theory, I like asymptotic theory, so I decided I need to talk about this beautiful part of the analytic theory of multiple orthogonal polynomials. So what are the ingredients and the tools? And again, I had a dilemma how to start, and I like electrostatic interpretation because I find it very elegant and interesting. So when we're studying polynomials, obviously, especially we're studying monic polynomials, it's equivalent to studying their zeros, where the zeros are, or at least where the bulk of the zeros is, and how they behave when the degree grows to infinity. And there is a standard idea from more than a century already, consider the zeros as charged particles and see how they behave. So we're assuming zeros are on the plane, which are complex analysis, and a single charge on the plane creates a potential given by a logarithm. So the force, which is a gradient of potential, it's inverse to the distance. If the charge is of size E, it's E times the logarithm. So if we have a finite number of charges, it's a superposition principle. The potential is given by the sum of these individual contributions. And the mutual energy of these particles, it's essentially double sum of this logarithmic interactions between masses at the point AJ, multiplied each time by the size of the charge. So in this setting, there is a beautiful work of Stiltius about Jacobi polynomials. So Jacobi polynomials are an extended family of Chebyshev polynomials. They include a lot of very nice, important polynomials, Legendre, and so on. And they are orthogonal on -1, 1 with respect to the weight 1 minus x power alpha, 1 plus x power beta. Alpha and beta should be greater than -1 to be integrable. And for this polynomial, Stiltius in 1885 gave the following beautiful electrostatic interpretation. So take the n zeros of these polynomials. We know they are simple. They'll live on the interval -1, 1. Assume they're charges, each charge of size 1 plus 1. So they're repelling each other. Look at the minimizer of the total energy. They stable equilibrium, these charges. You allow them move freely on -1, 1 until they settle down in equilibrium. But equilibrium is this energy that it's written right here. So if we look at this energy, we see there is a component, the first term, it's essentially the mutual interaction that I already discussed before of size. So everybody is a size 1. There is an extra term here that we call the external field. It's given by this function phi, written explicitly right here. So we see that this external field, it has two components again. So one component we call like a main component. It's basically comes from the orthogonality weight. So it's logarithm of 1 over square root of W. The second component is a correction. It's a very small correction that can be seen here like two fixed charges at the endpoints of size 1/2. Now, they settle down in equilibrium. So you drop these charges moving, as I said, freely on -1, 1. They have the external field acting on them, given here. They have mutual repulsion, and they move, they adjust until they settle down in equilibrium. This will be the zeros of your Jacobi polynomial of degree n. It's a beautiful interpretation. Now, it also allows us to guess, if not proving rigorously, at least to guess what is happening when n goes to infinity. The number of charges is increasing, right? So for each individual n, we had the minimal energy. We hope we can carry over this minimization property to the infinity. But now we look at the energy, we see that the first term has, roughly speaking, n squared components or terms. The second one has only n, so the first one dominates. So when n goes to infinity, we essentially will be minimizing only this part. The discrete potential becomes a continuous potential. It's just the integral of this logarithmic kernel. The discrete energy becomes the continuous energy. So in the limit, the distribution should minimize the energy, this energy here. And that's the right answer. And this energy, this minimizer is well known. It can be written explicitly. It's written right here. And we call in potential theory the minimizers of the energy or settle point of energy, we call equilibrium measures. So this is the equilibrium measure of the interval -1, 1. And this is the way the zeros in the limit of Jacobi polynomials, not only them, but particular Jacobi polynomials, they behave. So this measure actually could be found from a very important property. If we look at the Cauchy transform of this measure, we see that it solves the quadratic equation. By the way, let me just mention that living on the complex plane, being a complex analyst, this is a very nice trick. So instead of working with measures, which is typical real analysis object, you consider Cauchy transform of this measure, which is now an analytic function in general. And now you say something about the Cauchy transform and eventually go back to the measure. So in this case, the Cauchy transform solves a quadratic equation. It's the simplest instance of algebraic equation we can figure out. Well, except the trivial of degree 1. Okay. So what about multiple orthogonal polynomials? Can we figure out a certain electrostatic model? Again, I showed electrostatic model for Jacobi polynomials, a very particular case, right? Here again, don't expect to have a general electrostatic model, but in some specific cases, we do have, and it's a work in progress with Ramon Uribe and Joaquin Sanchez Lara in Spain. So this is the situation. Let's consider the Angelesco case. When these two weights are nice, remember what is happening, the weight W1 is living on the left, W2 on the right. In this case, it's pretty easy to show that zeros of harmonic polynomial Pn split in the right way. So N1, which is number of orthogonality conditions on the left, zeros go to the left, N2 go to the right. They will be interacting. They all have charge 1. So they have certain repulsion, right? But it turns out that the equilibrium is not totally described by this. There is an additional set of conditions. First of all, external field. You have an external field, again, coming from the weight. No surprises here. And then you have something else. Turns out you will have certain charges of size -1/2 that's sitting, interlacing. So we're focusing now on the guys on the left. They will be in equilibrium from the mutual interaction, the external field, the interaction with their neighbors, red neighbors on the right, plus certain ghost charges sitting interlacing of size -1/2 on the right. Now we can try to make the guess. What is happening when the multi-index goes to infinity in a proportional way? So when N1 over total N1 plus N2 goes to theta 1 and so on. Well, we know that the number of charges on the left will be proportional to theta 1, on the right to theta 2. So when n's go to infinity, they should be described by two components now. Lambda 1 describes the asymptotic distribution on the left, lambda 2 on the right. The size of lambda 1 and lambda 2 is prescribed by this limit, so we already discussed that. Now, what about the interaction? It turns out that what we saw is the following. The interaction, so the way they repel the guys on the left, each other, is with the size 1. They all are equal. Now, they still want to repel the guys on the right with the size 1, but it's diminished by the interlacing of the size -1/2. In the limit, this interlacing becomes just the same distribution. What is happening at the end, that these two components, lambda 1 and lambda 2, will be in equilibrium, but it's a vector equilibrium. That is expressed in terms of this matrix that's called interaction matrix. It says that people from the same family repel each other with the force 1, but people from the opposite families, they repel each other, but with half of the strength. So you solve this vector equilibrium, which is not trivial, and that will be the right asymptotic distribution for the Angelescu case. So what is happening in the Nikishin case? Now we know that all zeros live on the left, where both W1 and W2 reside, right? So everybody lives there. The interesting fact, there again will be certain ghost charges of size -1/2. And the number of these charges is the minimum of N1/2, the smaller of this. Now, what is happening? How we describe the asymptotics? Again, we need two components. One component of the measure will describe the distribution of the red dots, the zeros of my polynomials. We know that in the limit, the total size is 1, basically, roughly speaking, right? The other component will describe the distribution of these ghost charges on the right. And the size is the smallest of these two numbers, theta 1 and theta 2. What is the interaction matrix? We see now these guys no longer interlace. They are still sitting there negative. So we see that the vector equilibrium we got now is given by this matrix, which says that you repel, you hate the members of your own family with a strength 1, and you are attracted by the members of the other family with the strength 1/2. Well, it happens, you know, Capuletti, Montesquieu, and so on. So this is interaction matrix for Nikishin system. If we want to move to more complex situations when we have non-Hermitian orthogonality, and this slide already appeared basically in Guilherme Silva's talk, and it's something that we have publication on that. Now we have, I go very briefly, we have non-Hermitian, everything more complicated. Although the weights are nice cubic weights that appear here, we have integration and complex plane. And these polynomials of type 1, where we have, as I said before, a combination of two weights, or of type 2, when we split the conditional orthogonality between two weights, or better to say here, two contours, now the geometry is much more complicated. And again, Guilherme had a much better animation than I have. But if you wanted to take a total degree 100 and move how many conditional orthogonality you have on the first measure, and you see how zeros of the three sets of polynomials behave. It's a very complex and geometrically very interesting behavior. If you want to describe it, now it turns out you need three components. It's again vector valued equilibrium, but now you need three measures. You need also an external field, which is fine. It comes from a certain rescaling with it, and the z cube comes from the weight of orthogonality. But what is essential here, we have a 3x3 interaction matrix where you can recognize the typical Angelescu component, and also you can see the typical Nikishin component, which makes sense because, have you seen in this geometry, we had times when zeros were separated, typical Angelescu, and when they lived all together, typical Nikitian. So this matrix allows us to study in these asymptotic conditions with additional, more or less complicated additional constraints on the size of the measures. Now, the way we work on it, as I said, instead of looking at measures, we look at their Cauchy transforms, and then very important result that if you combine these Cauchy transforms correctly, they turned out to be solution of the same cubic equation that we call spectral curve or loop equation. Great. So you know that cubic equation shouldn't be studied on the plane. It should be studied where it's a natural habitat, which is a Riemann surface. So we use this Cauchy transform to build a global meromorphic solution on this Riemann surface. And the way it goes from there is the following. So in order to prove existence of this extremal measures, vector equilibrium, and describe the properties, we use certain objects from geometric function theory that call trajectory quadratic differentials that we have to follow on the Riemann surface. So it's really fantastically beautiful, complex analysis study. There's alternative, but still using Riemann surfaces. You cannot avoid Riemann surfaces, so-called Nuttall approach, and Doron Lubinsky gave his talk. He mentioned John Nuttall, where you essentially start from a Riemann surface. You build the Riemann surface with a very specific sheet structure, and from there you can again obtain asymptotics. Let me just mention, okay, so you imagine you got the structure of your equilibrium measures. Now what? How do you prove everything rigorously? We have a new tool we've been playing for the last 20+ years. It's a beautiful tool, beautiful toy. It's called the Riemann-Hilbert formulation. So for instance, for the type 2 multiple orthogonal polynomials, remember given by the split conditions, we can shift the paradigm. And this is was done first in the work of Geronimo, Coilers, and Vanasse, but it was based on the founding fathers' work by Persidite, Thanasis Focus, Aids, Joe, and other people. And essentially it says, instead of studying orthogonality, look at this matrix valued functions for which we know the boundary conditions. So imagine that on support of these measures of orthogonality, we have a condition on the boundary that says that this limit values, boundary values on the left and on the right of this 3×3 matrix are related by this nice non-commutative condition. It's a very simple condition where the orthogonality weights appear explicitly. Plus the orthogonality conditions N1 and 2 come in the second assumption, behavior at infinity. They're sitting right here. It's a diagonal matrix. You need to add some local conditions just to ensure uniqueness. That's not important right now. And the thing is, if you find the Y matrix that solves this problem, the 1 entry, it's exactly your polynomial. Turns out that for type 1, remember this object Q, right, that we had here, this join, we have a similar problem. Now we're looking for a matrix X, 3×3, very similar boundary values conditions. And the first row of this matrix gives you the components A that we're looking for. That's great. So let's compare. So when we see the type 1, this is the boundary value problem we need to characterize. Type 2, these are they appear here. If you compare, you can go transit from one to another, essentially by transposition, taking inverses, which immediately gives you the relation. It's called Malloy relation between matrix X and Y, and gives you duality between type 1 and type 2, which is great because it allows you to prove a lot of stuff for type 1 if you know already for type 2 and so on. Then you can also use a Riemann-Hilbert for asymptotic analysis. By the way, you can use it to develop other properties. But asymptotic, you start from a matrix, say Y, you make transformations which are invertible, and explicit, you arrive at the matrix which has almost no jumps. and identity and infinity, you conclude that this matrix is identity. And then you invert all these transformations, and then you have something about this matrix Y, and it means about the polynomial. So in your analytic toolbox, and nowadays you will need potential theory, vector equilibrium, you need algebraic functions, Riemann surfaces, quadratic differential Riemann surfaces, Riemann-Hilbert problems, and spectral theory of self-adjoint operators. Okay, so let me go very quick to some application. I promised about applications. And here I was too optimistic when I wrote this slide. I said, I will speak about number theory, rational approximation, and so on and so forth. No way. So first let me introduce very quickly speak about rational approximation, because the motivation of this polynomial, original motivation, one of them is approximation. Doran Lubinsky gave a beautiful talk about Padé approximants. Let me remind you. So we start from a germ, analytic germ of infinity function. We want to approximate it by rational function. We linearize the problem, essentially. So we choose the degree and we look for a polynomial Pn of degree up to n such that this combination, P times F minus another polynomial, we kill as many coefficients at infinity as possible. We start essentially at 1 over z power n plus 1. So these B and P are not unique, but their ratio is unique. It's called NN-PADÉ approximant. And using standard complex analysis, it's very easy to show that Pn satisfies certain non-Hermitian orthogonality conditions, but under some additional assumption on F, it's actually satisfy Hermitian standard orthogonality conditions. Simple exercise, start with this series that I wrote there. In the polynomials, Pn denominators will be Legendre polynomials that you all know and cherish. If you do it for such a nice function and you plot the zeros of the denominator, the poles of the approximant, you get this beautiful picture. You see that zeros are drawing certain curves. The origin of this curve is very simple. You're trying to approximate a multivalued function f with single valued objects, which are rational functions. So they have to make cuts, natural cuts on the plane. And it was Haber-Stahl who originally explained this cuts, the external properties of this cuts, and so on. It's a beautiful theory. Now, what happens if you still want to recover more than one value of the function f? It's multi-valued. So there is so-called SHAFER approximation, the 70s. SHAFER had the following idea. So imagine now you generalize the idea of Padé, and now you develop at infinity not just polynomial plus polynomial times f, you extend it to quadratic. So you add another term. So combine in such a way that you kill as many coefficients as you can, and then imagine that what you have at infinity, it's not a zero expansion, but just 0. So equate the right-hand side to 0. It's a quadratic equation. We know how to solve it. You have two values for the solutions, and you can expect that these two values recover at least two values of the function. It's not always the case. They don't work very well. They're complicated to handle, but the idea is nice. And if you look at this combination, this is actually a particular case, what we call Hermite-Padé approximants of type 1, when we combine polynomials for different functions. Now we have like two different functions, analytic germs at infinity. So if, for instance, if I plotted for the following, for the following two functions, and I plot the zeros of this, well, it's not my plot, it's Sergei Sweden's plot, and you see how complicated the geometry becomes in this case. In this case, we have, again, type 1 orthogonality conditions. We could also have type 2 when you want to approximate two different functions with two different rational functions, but with the same denominator. And in this case, you get type 1 multiple orthogonal polynomials. So these are very much connected. So let's go back to this idea that I mentioned. We want to do analytic continuation of my function that I know it's multi-valued. Imagine it's algebraic. But I want to recover not only the first value, but all possible value of this function. So we saw Stahl show that Padé approximants are not good for that. We need to go further. And Sergei Swedin recently had a very nice discussion example of the paper in the archive. He said, well, if we're dealing with algebraic function, taking powers of this function might reveal their hidden branch points. So let's combine type 1 and type 2 Hermite-Padé approximants, and we can actually recover things. So he started with type 2 Hermite-Padé approximant to the set of function f squared f cubed, and he showed that he's able to recover, as you could expect, the value on the first sheet. Then he turned to type 1 Hermite-Padé approximant for the function f squared f cubed. So look at this as a cubic equation, right? And then the ratio of n0 over n2 allows you to recover the sum of the three solutions, of the three sheets. You have the sum. And then he had a very clever trick how to combine these a's for different n's to recover the sum of two sheets. Now you see we have 1, 3, and 2. You have recovered everything. And there is a nice application in the AC power flow problem, and I'm bringing it here in case an engineer is hiding in the audience. So the power grid is an extremely complicated dynamical system, but it's governed by very simple laws. In each node of the Kirchhoff's current law, when you write everything down, it's a system of nonlinear algebraic equations, and the engineers care about so-called voltage collapse, for which value of the parameter you can have unfeasible solutions. And there are several ways of doing it using standard techniques. But not so many years ago, Spanish engineer Trias figured out a method he called holomorphic embedding load flow, Helm method, which essentially says add a parameter, complex parameter, show that the solution you're looking for, it's an algebraic function in this parameter, and use the analytic continuation. It's not a homotopy method, it's just direct analytic continuation. How do you do that? Trias uses Padé approximants. But it turns out that sometimes the solution you're looking for, physical solution, is not in the sheet that you're started from. You need to go to the other sheet. Well, Swedin and Bachorsky, they try to use Hermite-Padé approximant to solve this AC power flow problem. Very interesting development. Okay, very quick. I know I'm basically the discount time. Number theory, I will go very fast. Essentially, I basically will skip this part. You can prove irrationality of things. For instance, if you start with this two nice, very simple function f1, f2 that can be evaluated at I, and that correspond to Angeleska system, essentially, and you write the type 2 multiple orthogonal polynomials, that means the denominator is the same for both functions, and you combine these conditions, you add these two conditions, the fact that the polynomial here is the same allows us to rewrite this condition like this, evaluated at I. And also you killed this log and only pi remains. Now, everything is kind of explicit here. You can show that this guy, it essentially has integer coefficients. B also have integer coefficients. So everything kind of integer here up to pi. On the left, you also can work out to show that it's non-vanishing. So if pi, oh, and by the way, not only non-vanishing, going to 0. So if we assume that pi is rational, we would have like a sequence of integers, non-vanishing integers going to 0. Impossible. It means that pi is rational, is irrational. So Hermite would claim here immediately, I also did something similar, is the way introduced to prove that E is transcendent. Also, Apperi, when he proved that zeta 3 is irrational, basically used these ideas, although not explicitly, and so on. My last example is interacting particle. So imagine only two examples I've been working on. So you have certain, let me draw this picture. You have paths doing random walks. So it's a random process, so-called square BESSEL process. The only condition, they start from the same point, they end up at the same point, and they never collide. And you want to describe this for instance, take a snapshot to describe distribution of the path. Turns out the so-called multiple orthogonal polynomials. It means you need multiple orthogonal polynomials type 2 to describe what's going on both in the bulk or at the edge. And this is work with Arno Koilars, Frank Jablonski, and other people. Or as was mentioned in the talk by Guilherme Silva, if we study random matrices, and we have so-called random matrices with external source, where we have an addendum here, certain matrix A, that makes everything more complicated because it's no longer a unitary ensemble, and you want to study the eigenvalues in the bulk, it's a probabilistic, you need to know how it distributes. So equivalently, you need to study the average characteristic polynomial. How can you describe it? Well, in the simplest case, you can say, well, imagine my external source has only two eigenvalues, A1 of multiplicity and A and minus A. And the size of the matrix goes to infinity. So in the random matrix model, we want to see what's happening when n, the size, grows to infinity. It's been studied by many people. Here I only put some of them. You can see Aptekarov, Ken McLaughlin, Pavel Breher, Arno, Guilherme, and so on. And the crux of the matter is that this guy here, my characteristic polynomial, is multiple orthogonal polynomial. So if we want to describe all the statistics and the limit, and by the way, in particular case of V being x squared is just a multiple Hermite that I showed at the beginning. So now we know the path. So the only thing we need to do is go to study asymptotics of this multiple orthogonal polynomial, use your vector equilibrium in the plane, Riemann surfaces, multiple trajectories, and so on and so forth. And you get the statistical problem solved. Okay, this is the summary. I know I ran out of time. 3 more minutes. First of all, this is very brief summary. So this multiple orthogonality addresses several measures or weights simultaneously in different ways. It has natural origin in number theory, approximation theory, but as you could have seen, there has many applications, and I will mention a few more now. It has very non-trivial analytic theory, which is lagging far behind the theory of orthogonal polynomials, because it's more complex. And I would say that stable numerical implementation is infancy. Sergei Sweden been doing important work, Bernd Beckerman, and I know also a lot of Reichel did something, but essentially we are just starting from zero. Things I didn't mention. I have no time. You would need another hour for that. Discrete multiple orthogonal polynomials when you have measures instead of weights. Relation to discrete integrable system, ask Walter Vanessa about that. Isomonodromic deformation, Paine-Levé equation, there's a team of Japanese mathematicians developing this. So-called reordered arrays, infinite matrices, Gauss type quadrature and application. Again, Walter or well, other people have contributed here. Singular value of products of random matrices, you need multiple orthogonalities. Planar orthogonal polynomials that can be written as multiple orthogonal polynomials, and they describe so-called Hellishov flows and two-dimensional growth models. Beautiful and very active field of research. So I also wanted to add a number of names here, not only a picture I showed before, but people that contributed. And honestly, after 2 slides, I stopped. I cannot do it. A lot of people, many of them in the audience, did a lot. And this is my final message, essentially for young people. This is a hot topic. It has a very exciting applications. The theory is developing, numerics starting from zero. So don't miss your chance. This is a great subject to work on. Thank you very much.
Thank you, Andre. Are there any questions? I don't see any questions, so it just remains to thank you.
Oh, well.
There's none in the
I'm no longer sharing my screen, is correct?
Yes.
Okay.
Okay, so I think it just remains to thank Andre again for his great talk. Thank you, Andre.
Thank you very much. Thank you, Peter. Thank everybody for attending this talk. Stay safe.